Welcome to Chapter 1, Section 3, Fields. In this section, we introduce the algebraic structure known as a field. Fields give us the precise rules for addition and multiplication that underlie the real numbers, the rationals, and the complex numbers. We will also define ordered fields, which combine algebraic and order structure. Let's get started. Here is our roadmap for this section. We will begin with the definition of a field and its axioms, then explore the immediate consequences of those axioms. After that, we will introduce ordered fields and prove the basic properties of inequalities. Let's dive in. Before we can do analysis, we need to know exactly what operations are available and what rules they follow. The concept of a field gives us this precise algebraic framework. It captures the essential properties of addition and multiplication. The rationals, the reals, and the complex numbers all share the same basic algebraic structure. By proving results at the level of fields, we prove them once and for all, rather than repeating the work for each number system separately. Finally, we will combine the algebraic structure of a field with the order structure from the previous section to get an ordered field. Ordered fields are where inequalities live, and they provide the natural setting for the real number system. Let's begin with the definition of a field. A field is a set equipped with two operations, addition and multiplication, that satisfy a specific list of axioms. These axioms are organized into three groups: the addition axioms, the multiplication axioms, and the distributive law that links the two operations together. Let's look at each group in turn. The first two addition axioms are closure and commutativity. Closure says that adding two elements of the field always gives another element of the field. Commutativity says the order of addition does not matter. These are familiar properties from ordinary arithmetic. Next come the structural axioms. Associativity tells us that grouping does not matter when adding three elements. Axiom A4 guarantees the existence of an additive identity, the element 0, which leaves every element unchanged when added to it. One more axiom completes the picture for addition. The final addition axiom guarantees that every element has an additive inverse, denoted -x, whose sum with x is 0. Together, these five axioms say that the set F under addition forms what algebraists call an abelian group. Now let's see the multiplication axioms. The multiplication axioms mirror the addition axioms almost exactly. M1 says the product of two field elements is again in the field, and M2 says multiplication is commutative. So far, the pattern is the same as for addition. Let's see the remaining three. M3 gives associativity of multiplication. M4 guarantees a multiplicative identity, the element 1, which must be different from 0. This requirement that 1 is not equal to 0 ensures the field has at least two elements. One more axiom to go. M5 says every non-zero element has a multiplicative inverse. Notice the key difference from the addition axioms. 0 does not have a multiplicative inverse. The non-zero elements of F under multiplication also form an abelian group. One more axiom ties addition and multiplication together. The distributive law is the single axiom that connects the two operations. Without it, addition and multiplication would be completely independent structures. This law tells us that multiplication distributes over addition. which is the familiar rule we use when expanding expressions like a times the quantity b plus c. This diagram summarizes the structure of the field axioms. On the left, we have the 5 addition axioms, which make the set an abelian group under addition. On the right, the 5 multiplication axioms make the non-zero elements an abelian group under multiplication. The distributive law at the bottom is the bridge connecting the two operations into a single coherent structure. Next, let's note some useful conventions and examples. Remark 1.13 Part A introduces the standard shorthand notations we use in fields. Subtraction is defined as adding the additive inverse, and division is defined as multiplying by the multiplicative inverse. Similarly, x squared means x times x, and 2 x means x plus x. These are all abbreviations built from the 2 basic operations. With this notation in hand, let's see the most important example of a field. The most familiar example of a field is the set of rational numbers Q. All the field axioms hold for the rationals with their customary addition and multiplication. So Q is a field, and everything we prove about fields in general will automatically apply to the rationals. Part C of Remark 1.13 explains why we bother with this abstract setup. Many familiar properties of the rationals, such as cancellation laws and sign rules, are actually consequences of the field axioms alone. Once we prove them at this level of generality, we will not need to reprove them when we construct the real numbers or the complex numbers. Let's now see what the field axioms imply. Proposition 1.14 lists 4 consequences of the addition axioms. Part A is the cancellation law for addition. If x plus y equals x plus z, then y must equal z. Part B says that the additive identity 0 is unique. If adding y to x gives back x, then y must be 0. Part C says the additive inverse is unique. The only element that sums with x to give 0 is negative x. And Part D is the double negation law. Negating x twice gives back x. Let's prove these statements. Before we dive into the details, let's see the big picture. The core result is Part A, the cancellation law. Once we have that, Parts B, C, and D follow as special cases. Part B comes from setting z equal to 0 in Part A. Part C comes from setting z equal to negative x. And Part D follows from Part C by replacing x with negative x. So the real work is in proving Part C. Here's the proof of Part A. We start with y, rewrite 0 as negative x plus x using axiom A5, then use associativity to regroup. At the crucial step, we swap x plus y for x plus z using our hypothesis. Then we regroup again and simplify using A5 and A4 to get z'd. Every step uses only the addition axioms and the hypothesis. Parts B through D all follow from the cancellation law. For Part B, the equation x plus y equals x is the same as x plus y equals x plus 0. So y equals 0 by cancellation. For Part C, x plus y equals 0 is the same as x plus y equals x plus negative x, so y equals negative x. For Part D, we know negative x plus x equals 0, and by Part C, this means the element that sums with negative x to give 0 must be x, so the negative of negative x is x. Proposition 1.15 states the exact same cancellation laws, but for multiplication instead of addition. The requirement that x is non-zero is essential, since 0 does not have a multiplicative inverse. The proof follows the same pattern as the proof of proposition 1.14. Prove part A by multiplying both sides by 1 over x. Then derive the rest as special cases. Rudin omits the proof because it is so similar. Let's see the analogy more clearly on the next slide. This table makes the parallel between propositions 1.14 and 1.15 explicit. Every statement about addition has an exact counterpart for multiplication. You just replace plus with times, 0 with 1, and negative x with 1 over x. The only difference is that the multiplication versions require x to be non-zero, since 0 has no multiplicative inverse. This symmetry is not a coincidence. Both addition and multiplication give abelian groups, so they satisfy the same abstract cancellation laws. Now let's see what happens when we use both operations together. Proposition 1.16 gives 4 more consequences of the full field axioms. Part A says that 0 times anything is 0. This seems obvious, but it actually requires proof because the axioms only tell us about the additive role of 0, not about what happens when we multiply by it. Part B says a product of non-zero elements is non-zero. This is sometimes called the absence of zero divisors. 2 more consequences are coming next. Part C is the sign rule for products. Negative x times y equals the negative of x times y, and the same holds if we negate y instead. Part D says that negating both factors leaves the product unchanged. Let's prove each of these. The proof of part A is elegant and short. We use the fact that 0 plus 0 equals 0, which is just axiom A4. Multiplying both sides by x and applying the distributive law gives 0x plus 0x equals 0x. Now recall proposition 1.14 part B, which says that if x plus y equals x, then y must be 0. Here, 0x plays the role of both x and y, so 0x must be 0. This is the first time we have used the distributive law, and it is the bridge that lets us connect the additive property of 0 with multiplication. For part B, we use proof by contradiction. Suppose x and y are both non-zero, but their product is 0. Since x and y are non-zero, their multiplicative inverses exist. Multiplying both sides of x, y equals 0 by 1 over y times 1 over x. The left side simplifies to 1, while the right side is 0 by part A. So we get 1 equals 0, which contradicts axiom M4. Therefore, the product x, y, cannot be 0. To prove that negative x times y equals negative of x, y, we show that their sum with x, y, is 0. By the distributive law, negative x times y plus x times y equals the quantity negative x plus x times y, which is 0, times y, which is 0 by part A. Now recall proposition 1.14 part C, which says that if x plus y equals 0, then y is the additive inverse of x. Applying that here, negative x times y must be the additive inverse of y. The second equality follows by the same argument with y negated instead. Part D follows from 2 applications of what we have already proved. Recall that part C tells us that negating one factor is the same as negating the whole product. By part C, negative x times negative y equals the negative of x times negative y. Applying part C again, x times negative y is the negative of x, y. So we have the negative of x, y. And recall proposition 1.14 part D, the double negation law, which says the negative of x, y, is just x, y. Notice that this result holds in any field, not just ordered fields. We have not used any notion of positivity here, only the algebraic axioms. The familiar sign rule from arithmetic is a purely algebraic consequence. Now let's add order structure to our fields. An ordered field combines the algebraic structure of a field with the order structure from the previous section. Two compatibility conditions are required. First, adding the same element to both sides of an inequality preserves the inequality. Second, the product of two positive elements is positive. Elements greater than 0 are called positive, and elements less than 0 are called negative. The rationals Q are the primary example of an ordered field we have seen so far. This diagram shows how the concept of an ordered field brings together two structures we have already defined, a field and an ordered set. The two compatibility conditions shown in the box at the bottom ensure that the algebraic operations respect the ordering. This combined structure is what allows us to work with both equations and inequalities in a consistent way. Let's see what these compatibility conditions look like. Let's see what properties follow. Proposition 1.18 lists the fundamental properties of ordered fields. Part A says that positive and negative are linked through negation. The negative of a positive number is negative, and vice versa. Part B says that multiplying an inequality by a positive number preserves the direction of the inequality. But what happens when we multiply by a negative number? Part C is the complementary rule. Multiplying by a negative number reverses the inequality. This is the familiar rule that multiplying both sides of an inequality by a negative flips the direction. Two more properties round out the picture. Part D tells us that every non-zero square is positive, and since 1 equals 1 squared, we get that 1 is positive. Part E says that taking reciprocals of positive numbers reverses their order. These are all rules you have used many times, and now we will prove them rigorously from the axioms. To prove Part A, suppose x is positive, meaning 0 is less than x. By definition, saw point 17 Part I, we can add negative x to both sides of the inequality 0 less than x. On the left, negative x plus 0 equals negative x. On the right, negative x plus x equals 0. So we get negative x is less than 0, which means negative ex is negative. The converse direction, that if x is negative, then negative x is positive, works the same way. Start from x less than 0 and add negative x to both sides. Let's continue with Part B. For Part B, we need to show that multiplying a strict inequality by a positive number preserves the direction. Since z is greater than y, z minus y is positive. Multiplying two positive numbers, x and z minus y, gives a positive product. So x times z minus y is positive, which means xz is greater than x, y. This is exactly the rule we wanted. Next, let's handle the case of multiplying by a negative. Part C handles the case where we multiply by a negative number. Since x is negative, negative x is positive by Part A. Since y is less than z, z minus y is positive. So the product of negative x and z minus y is positive by the ordered field axiom. Using the sign rule from proposition 1.16 Part C, this means the negative of x times z minus y is positive. So x times z minus y is negative, meaning x, z, is less than x, y. The inequality is reversed. Now let's prove the result about squares. Part D has two cases. If x is positive, then x times x is the product of two positive numbers, which is positive by definition 1.17 Part 2. The axiom that says the product of two positive elements is positive. If x is negative, then negative x is positive, so negative x squared is positive. But recall proposition 1.16 part D, which says that negative x times negative y equals x, y. Setting y equal to x, we get negative x squared equals x squared. Either way, x squared is positive. Since 1 equals 1 squared, we conclude that 1 is positive. This is a remarkable fact. The positivity of 1 is not an axiom, but a consequence of the other axioms. One more property to go. Reciprocals. For part E, we first show that 1 over y is positive. If 1 over y were 0 or negative, then since y is positive, their product y times 1 over y would be at most 0 by parts B and A. But y times 1 over y equals 1, which is positive by part D. That is a contradiction, so 1 over y must be positive. The same argument shows 1 over x is positive. Now multiplying both sides of x less than y by the positive number, 1 over x times 1 over y preserves the inequality and gives us 1 over y is less than 1 over x. Taking reciprocals of positive numbers reverses the order. Let's review what we covered. A field is a set equipped with addition and multiplication that satisfy 10 axioms plus the distributive law. The addition axioms and multiplication axioms each give the structure of an abelian group, and the distributive law connects them. We proved that familiar algebraic properties, such as cancellation laws, the uniqueness of 0 and 1, and sign rules like negative times negative equals positive, are all consequences of the field axioms. We do not need to reprove them for each specific field. An ordered field combines the field structure with a total order that is compatible with both addition and multiplication. This is the natural setting for working with inequalities. In every ordered field, non-zero squares are positive. 1 is positive. Multiplying by a negative reverses inequalities, and taking reciprocals of positive numbers reverses their order. In the next section, we will construct the real numbers as an ordered field with one crucial extra property, the least upper bound property. This is the property that fills the gaps in the rationals that we identified in the introduction. See you there.